Hello everybody. Yeah, thanks a lot to all the organizers. I think the organization has been wonderful since yesterday. We are really enjoying every bit of it. Thanks a lot to Naresh for that kind introduction. And now without further delay, I will sort of begin this lecture with some fishing ideas so that you are all set to have some fish maybe after the talk. All right, so let's start. I think today morning already we heard two lectures, two talks, one by Anuprita and another by Prayush, and I think they have set a right stage for my talk. I think you might see a lot of images which they have already flashed. So, I think this lecture might help you to crystallize some of those ideas and some of those things which we play with in gravitational wave astronomy. Okay, so some of the results which I will be showing in this talk are part of the LIGO collaboration, and the title of my talk is Diversifying the Net to Fish the Short Duration Transients from Merging Black Holes. So, here I just want you to emphasize, sort of pay attention to few things. Let me just see. Here I just want you to pay attention to a couple of words. One is the short duration diversification. So, here I will be talking about different ideas which we explore when we look for short duration mergers in the LIGO data. Yeah, so let's sort of go do a little recap so that we come to the main point very soon. So, just to remind all of you, this was our first binary black hole merger event which was observed with the two LIGOs, and what you need to essentially see is the time frequency distribution of the event. So, you can see that the frequency sort of progressed as the time lapsed, and this is typically what we call as a chirping behavior of the signal, and which is depicted in this waveform. So, as the frequency, as the two black holes, essentially they are in the binary orbit, they come close to each other and they increase the frequency emitting the gravitational waves, and finally they merge. Now, this signature essentially is typical for the stellar black hole binary mergers, but as you go to massive black holes, black hole merger, then essentially you have very less number of cycles in the inspiral phase, and what you see is only some kind of short duration signal. Okay, that is what I would be talking about subsequently. Of course, this event was quite spectacular, and which was sort of, it was the fastest Nobel Prize in physics, which was given to three pioneers of gravitational waves, and it was spectacular in many ways. It was first direct detection of gravitational waves, it was first direct observation of stellar mass black holes in a binary system, and it was the first direct evidence of the collision sort of black holes in a binary system. And this is quite important because so far we have been observing black holes in X-rays through basically observing X-ray flux in from the accreting systems, and the indirect evidence essentially used to give us the mass of the central black hole in the X-ray accreting system, and we have never seen black holes which are above about 25 solar mass. In fact, I remember in my PhD days, we never used to simulate signals about 10 solar mass, because that was something which all of us used to think that, okay, I mean the black holes, the stellar mass black holes means something which is typically of tens of solar mass. All right, now the whole picture has changed with the 3 observations runs which we took right from 2015 all the way till March 2020. And in these 3 observation runs, the whole information which we got about the black hole population changed drastically. So, I think this is a picture which you have been seeing since morning today. So, these are basically the compact binary merger events which we have observed. Just to give you a context, I mean, if you take one straight line along in this plot, that sort of corresponds to a binary compact binary merger with 2 component masses and the final remnant mass. And here if you observe that the striking feature which you can see here is all these blue straight lines, they are basically compact binary merger events observed by the gravitational wave network. And you see lots of massive black holes we have observed. In fact, you can see here in the 3 observation runs, as the interferometers improved their sensitivity, we saw a large number of compact binary merger events. Majority of them were actually binary black holes. In fact, if you try to this thing, these are typically 90 events, and if we put sort of moderate to assess the confidence of the detection, put a false alarm rate. So, when we talk about false alarm rate, is essentially we try to assess that what is the probability that a given given event which we have seen must have come from, let us say, a noise. Okay? And when we say 1 per year, so that probability is basically the chance that the noise can give rise to such a merger is basically 1 in a year. And so, higher is this number is better, because that basically means that there is less and less chance that the event which we are observing is actually from the noise origin. Right. So, if you have this, then the numbers which we have here is basically 76 compact binary mergers, and out of this my main focus in the rest of the talk will be events which are very massive. So, these are the very massive events which is with the solar mass roughly above, let us say, 100 solar mass. We have found one confident massive event, and this essentially falls into the class of intermediate mass black hole. And this was quite spectacular discovery, which the event was, I mean, this was observed quite immediately with the beginning of the 3rd observation run. We observed this on 21st May in 2019, and the event was quite unique as compared to the first event. So, you can see here that the time frequency morphology of this event is like, it is quite localized, unlike the first event where you can see a nice chirping sort of behavior. Here you can just see a blob basically, and this is a time domain representation of this event. So, it was short, it was quite significant. So, both the detectors, LIGO, 2 LIGO detectors could observe this event simultaneously with good confidence, but there were lots of challenges in observing such systems. The main reason behind is that when you have something like these blobs, you can, if you look at this temporal signature, you can see that it is almost like a sine Gaussian profile. And in the instrument like interferometer, there are lots of subsystems which can give rise to sine Gaussian profile, I mean noises which of that origin. For example, this is one such noisy event which looks pretty similar as compared to this. And these are the challenges which we face when we try to detect massive black hole mergers. And in fact, this is kept us investigating for a long time. That we announced the discovery of this was almost in 2020, 2nd September. So, it was almost 1 year that we were trying to investigate, trying to understand first whether is it coming from the noise origin, and then trying to understand the parameters of this event. So, what did we learn from this discovery? Essentially, it was even quite interesting. So, it was the most massive black hole binary system with the remnant mass of 142 solar mass and the components of 85 and 66, and it emitted the power which was emitted in terms of gravitational waves is 8 equivalent to 8 solar mass. So, it was the first direct evidence of existence of intermediate mass black hole with mass less than 1000 solar mass, and it also showed evidence for mild precision. So, for example, when you talk about precision, when the spins are not aligned with the orbital angular momentum, then that gives rise to very complex feature of the signals, and this showed very mild signature of that. Okay, let us try to understand what are intermediate mass black holes. So, they are basically, I mean, people have predicted various formation possibilities of these systems. Namely, they could be direct collapse of, let us say, population 3 stars, which are very old stars, or you can give rise to such systems when there are mergers in a very dense environment like globular cluster or let us say galactic centers, where there can be hierarchy of mergers, and that can quickly form a massive black hole system. So there is also another channel, which is like if you can have multiple collisions of star in a young cluster. Okay, but I mean, these are basically various channels in which you can form intermediate mass black holes. Of course, different channels will give rise to different signatures when you observe them, and that is something which is interesting, which we try to sort of look for. Now, what is the story in the electromagnetic band? So, in the electromagnetic band, there are several intermediate mass black hole candidates. And when we say candidates, essentially the mass of this black hole is inferred, because you cannot make direct measurement. So, these are basically indirectly inferred, and there are various ways in which you can indirectly infer the central mass. So, for example, you can try to study the kinematics of the objects in the dense cluster, and based on that you can infer that at the center maybe there is a intermediate mass black hole. There are also things like people do mass extrapolation of the standard m sigma relation, which you apply in the supermassive black holes, and hence you infer, I mean, when you extend that for the clusters, then and then try to infer the mass. So, there are different ways people have found various candidates of this intermediate mass black holes. But gravitational wave astronomy actually gives us direct measure of the mass in terms of the signature which it leaves on the signals. Now, what are the peculiarities of this system which we observed? If you look at the component masses, which was basically 85 solar mass and 66 solar mass, and these component masses, they themselves are very high. And I mean, there are studies of stellar models essentially, which predict that in the black hole population there is something called as the upper stellar mass gap. So, that means you cannot form black holes in this mass gap, which is between 50 and 120 solar mass by the standard stellar evolution process. But however, we have found these two component masses in this mass gap. So, which basically makes us wonder that maybe these are not the first generation black holes, but maybe they are second generation black holes. Maybe they are formed because of some other earlier merger and so on and so forth. So, there are all these questions about what are the, I mean, how the components are formed, and that makes basically this merger event quite peculiar. Of course, you must have realized that in order to detect such short signals, we need to have better detection algorithms, and we also need to have better parameter estimation methodologies, which I think Prayush was just talking about, the numerical simulations, which essentially gives the signal which we use in the parameter estimation. So, you need to have better models to estimate the masses and the properties of the signal. Now, what are the observational implications of this intermediate mass black hole events? Of course, since it's clear that that would give direct implication on the stellar evolution models. So, it will put constraints on the models. It also will also understand better about this upper mass gap, black hole mass gap, which is currently the theoretical prediction of the black hole population. And of course, if we detect this, if you have noticed, the signal is essentially short. It does not have much in spiral cycles, but the most of the power is essentially in the merger and post merger signature. So, if you can actually find loud post merger, then one can probe black hole ring down modes, and of course, then the structure of the perturbed black hole, which is the most interesting. Fine. So, now it is clear that we need to, it is clear that our detectors, they are sensitive to intermediate mass black hole binaries, and hence the strategy should be to detect such short signals combating with the noisy glitches. And what are the different detection algorithms that we sort of exercise regularly. Just to this thing that I was just mentioning to you about these two different. So, this is the intermediate mass black hole and this is the noisy transient, and many times, and we have a large number of noisy glitches. I think Anuprita was mentioning about some of them, and one needs to really take special care in order to not misclassify the noisy transient as an astrophysical event. I mean, we have had a couple of experiences in sort of tracking this. For example, recently when we wrapped up this third observation run, I mean the search of IMBH in the third observation data, there is a one event which we could not confidently arrive at the conclusion because of similar nature, and so I think those who are interested can look into this paper and look at the appendix of this event. All right. Of course, since the signal is very short, there is a scope to have alternative interpretations, and there have been already publications about that, which I will talk about a bit later. So as far as the algorithms are concerned, we essentially take a multi-prong approach. So, one is the waveform sort of basically it is a model agnostic search, which is based on the wavelets. The pipeline is called as a coherent wave burst. So, essentially what it does, it projects the data onto the wavelet domain in all the three detectors, or in how many detectors you have, and then you try to coherently collect the pixels which are energetic, and then you apply the coherence, that is you apply the fact that there should be delay between the arrival of the signals, and then also the consistency between how the response of the detector is to a particular direction, etc., etc. So, you fold in all this information in this coherent wave burst search, and then on top of it we also devise. So, this is based on wavelets. So, the entire search is based on the time frequency and scale sort of representation. So, you also ask a question that how the glitches essentially look like in that representation, and based on that we try to develop some vetoes in order to sort of classify or distinguish between the glitches and the glitches which hamper the IMBH sort of searches, and then as compared to the signals. So, in fact, we had done some study when we were doing the search for such signals in the first and second observation run, and we did tune actually this pipeline appropriately based on different classes of glitches, and that was actually turned out to be very useful when the 1905-21 was detected. The second search is basically it's a model based search which is match filtering, which I think Anuprita was talking about, where we just essentially correlate the data. I think there is some video, I don't know whether. I think it's not PDF. Okay, yeah, something is happening here. Yeah, so you can see here this is the template and here there is a signal. So when it is essentially the template coincides with the signal, and if they are phase coherent, then you see a sort of a peak here because of the phase coherence. And this is the basic idea which is used in match filter. Of course, I think this was originally pioneered by Sanjeev and Satyaprakash long back. And still we use this, especially this idea is used when you do stellar mass black hole binary searches. Of course, there are a lot of additional things happen when, let's say, when you are trying to search this with, let's say, massive black hole binaries. Okay, so what are the lessons we learned when this detection happened? We found that the model agnostic search did excellent. I mean, it did a fantastic job with a very high sort of inverse false alarm rate. I mean, the chance of I mean, I just mentioned to you about what is the false alarm rate is, and the confidence which it gave was very high. But the match filter search did not win, and that was a big concern. And in fact, our group carried out the investigation, and we took it up as a challenge to sort of improve this search. One of my students led this exercise, and in fact we improved that significantly, which we later on published in a couple of years back, and it was applied on the third observation run. So when we applied that, essentially, so the main idea which we did is we tried to tune the template bank appropriately for the massive black holes, because otherwise it was looking at all kinds of stellar mass, also even NSBH and everywhere. And if you are looking at all sort of the entire parameter space, then the chances of that you get false alarms is very high, and that is exactly what was happening. So we tried to tune it appropriately for the massive black hole binary cases, and we also sort of improved on some of the noisy vetoes. So for example, if you have a glitch like this, then and you know what kind of signals you expect, then you try to sort of develop a veto so that you try to distinguish or add a veto parameter which can sort of get rid of those features. So we did this, and what we showed is that the sensitivity improved. In fact, the improved PyCBC bank increased the false alarm rate. I mean, now it became basically 370 as compared to 1 per year. So it was all fine. I mean, we also got the sort of new upper limits on the intermediate mass black hole binary, and according to that, one should see one merger event like IMBH per globular cluster in its lifetime. It was all improved, and it was very nice because then we have two searches which can look at the short duration massive black hole binary events. Okay, one is model agnostic and one is something which is specially tuned for this, but it's equally sensitive. All right. So now the question is that all this was essentially with something which is aligned spin, nice kind of signals. But now if you imagine that such systems are, I mean, one of the progenitor which is sort of most likely are crowded systems, which is like galactic clusters or centers of the galaxies, then you expect that the system is much more complex. It does not have enough time to shed its asymmetry, and as a result you might have system which is asymmetric masses, which gives rise to the more signal complexity, and that needs to be sort of captured in not only in the waveforms but also in the searches. So for example, if you have, let's say, two black holes which are not symmetric in masses, but there are symmetric systems, then you expect that there would be higher order modes, higher than the quadrupole, would be there in the signal, and that depends on various things. So, though the signal is weak, the signal is more complex, and as a result your template bank will not observe those signals. So, one needs to tune the bank accordingly. Also, if you look at the signal from, let us say, from the top, as you have seen here, like a face-on binary or the edge-on, then the signal, the features are much more different. So, for example, if you have a edge-on, your orientation is you are looking at the binary in this way, then the higher order mode content is much more. So, here is sort of a little example for that. So, if you, so you can treat this as, let us say, the mass ratio axis, and this is the inclination axis. So, as you increase the mass ratio, you can see that as the mass ratio increases, the complexity, you can sort of start seeing the second mode much more strongly, and the signature is much more complex. The same thing you can see if you sort of increase the inclination of the binary. So, and this is something which one needs to sort of, the searches needs to be tuned and captured. So we took here basically different approaches. So, one is to develop the match filter search along the similar idea as we had done for the sort of the quadrupolar mode, and extend it for the higher order modes. So, I am not going to talk anything more about this. Kaustav is going to talk in the parallel session on this work. And then the second idea which we explored was you use the sort of machine learning based idea using the convolutional neural network to try to distinguish between these complex signals and the noisy glitches. So, this was actually done by one of my project student as part of her BTech project, and the idea which was used is to use this time frequency morphology much more efficiently in order to do this distinguishing, do this kind of a classification between the noisy glitches and the signals. So, here there are salient features of THAMES. So, THAMES is transfer learning for higher order modes for asymmetric massive edge-on like systems. So, we took edge-on like systems and we tried to sort of train the signals as well as a large number of glitches, and then we essentially applied it. We also designed a very specific kind of test statistic which takes into account that if there is a glitch in one of either of the detectors, then essentially it should give a appropriate sort of weighting, and this statistic essentially will get translated accordingly. We also developed some new kind of noise vetoes which takes into account the glitch morphology, and when this was done and then we applied it on the third observation run data which was open, and we found that THAMES actually performs comparable to the bank which Kaustav developed for 1905-21 like systems. Right. So, so now the thing which is sort of, so when we have such a complex sort of crowded environment, we expect that you will have asymmetric masses. We also expect that the system will have isotropic spins. So, it will not be like the black holes will not be aligned with the orbital angular momentum, and when that happens then you have even additional sort of complexity. So, for example, when the let us say when your angular momentum, spin angular momentum, total spin angular momentum is not aligned with the orbital angular momentum, there is a spin orbit precession, and which gives rise to these extra modulations which you can see, and this needs to be captured in the detection algorithms. So, that is the next steps which we will take subsequently. So, there are two effects which one needs to take. One is a spin orbit precession, and as well as you might have binaries which may not be circular in nature, because so far all our algorithms, model based algorithms rely on the circular orbits, But of course, if you don't have enough time to sort of circularize, which may be the case when the system is in a crowded environment, then you expect that the binaries might be non-circular. So these are the two additional features, and of course, the real world is more complex, because in the real world you will have all these three features, and currently we do not have reliable waveforms to take care of all these three effects. Neither we have efficient sort of algorithms which also take care of all these effects. So this is something which needs to be done in future while our instruments are also improving in sensitivity. Okay, a small detour. So there have, as I mentioned earlier, that since 1905-21 was a short duration signal with no inspiral content, it was difficult to probe the chirp mass of the binary. It was quite challenging, and since the signal is very short, I mean there were alternative sort of interpretations of the signal. So two such interpretation, one was that it is indeed an asymmetric system, and in this interpretation the signal was actually the masses were 171 and 16 solar mass. Both of them are outside the upper stellar mass gap, and there was another interpretation where that this is actually an eccentric system. This was done using the numerical relativity simulation waveforms, and according to them, both the component masses, they are almost equal mass system, and both the component masses were actually sitting inside the upper mass gap. So it all looks interesting, because when you have short duration signal, there are lots of other effects. There are various ways one can sort of interpret. There are various depending upon the choices of the waveforms, the priors, I think the whole picture also can change. Okay, so now, so after talking about 1905-21, let's sort of change and look at the bigger picture, that what is it that we have learned so far from the O3 binaries, right. So what about the mass asymmetry, spins, eccentricity. So just sort of let's get a bigger picture. So the majority of these black hole binaries which we have observed, they are nearly equal mass. A large number of them essentially, so here we sort of talk about two mass gaps. So one is this lower mass gap, which is between 2 and 5 solar mass, and the upper mass gap is the one which I talked to you earlier, which is basically between 50 and 120. So of course you see lots of the remnant masses of these binaries falling in the upper mass gap, but you also see lot of some of the binaries, either the component or the remnant falling in this lower mass gap, which is the mass gap between 2 and 5. This mass gap is actually from the observations in astronomy, namely from the X-ray observations. Of course, there are questions whether, I mean, is this a real mass gap? Of course, I think with time we will know more about this mass gap. Of course, there could be biases in the X-ray observations, which is also an open question. Okay, so what about the astrophysical population? So here I have plotted the primary mass compared to the sort of the rate. So what you can see is that earlier people used to think that there is only one sort of power law distribution, but here you can see very clearly that there are more features here, and there is a multimodality feature observed, which was observed in also the second catalog, and which is consistently we observe in also in the third catalog. Further, if you just make the similar plot as a function of mass ratio, though majority of the systems which we have seen, they are equal mass ratio, there are few systems which have shown asymmetric mass ratios, and once you have that, then of course your whole profile sort of changes, even though I mean the rate is still sort of higher for equal mass system, and this also could be an observational sort of bias, because our detectors are, the waveforms or the signals themselves, they are more stronger for the equal mass system, and as a result, we do observe something which is much more stronger in, let's say, in SNR. How about spins? So, typically the way we capture the spins in gravitational astronomy is with respect to two parameters. One is what we call it as the effective spin. This is some kind of a weighted projection of, let's say, the aligned spin, individual spins with respect to the angular orbital angular momentum vector. Okay, so in some sense it is sort of a measure of alignedness of the system with respect to the orbital angular momentum. And what we observe is that majority of our population shows low mass of low values of effective spin, and this also we have seen consistently between the second catalog and the third catalog. What about the precision? Okay, there is another point to note here is if you look at the chirp mass versus the effective spin, then as you go to the lower chirp mass, you can measure the chirp mass more sort of accurately because you have in spiral, whereas when you go to higher masses, your measurement accuracy in the chirp mass also reduces. All right, so and then there is another parameter which captures the precision. So, which is you can sort of treat it, of course, in reality this is more complicated, but essentially you can treat this as the in-plane spin, effective in-plane spin, and that measures the precision of orbital precision of the system basically. So this plot is more interesting because with the second catalog, it appeared that it sort of favors more aligned spins because this is a cosine theta, which is close to 1. But as in this sort of new population, we have seen few systems with the mild precision, and you can sort of see now that this distribution is becoming more isotropic, and this is something new, and this is also interesting as far as we observe more and more events. Now coming back to the formation channels, so if you look at the isolated black hole binaries, essentially what you expect is that you expect the system to shed the asymmetry because it is isolated and is slowly sort of shed away its asymmetry while it is getting formed and hardened, and of course finally the merger takes place. Whereas when you have binaries in a crowded environment, you expect the individual spins to be sort of randomly oriented, as I mentioned earlier, and our current evidence sort of tends to support this isotropic spin distribution, so which is also sort of quite interesting. Okay, so does the observation reconcile with models? In the observation in the isolated binary evolution models, there is a prediction that your black holes will peak around 10 solar mass, and that was one of the reasons why all of us used to run things at 10 solar mass. Of course, this is modulo lots of other factors like how during the formation of this black hole, how the mass transfer is, natal kicks and star formation rate, and lots of other factors which decides this. But when you talk about the dynamical formation channels, like in the crowded environment, there are various sort of predictions. So for example, if you take globular cluster, then people have predicted based on the 3-body interactions that the peak would be above 10 solar mass. If you take, let's say, the young clusters, then it does not favor really 10 solar mass peak. And if you take, let's say, galactic nuclei, it can produce binary black holes with a wide range of masses because it has very high escape velocity, so it doesn't kick out. I mean, the kick velocity is not really higher than the escape velocity, and as a result the binary stays inside, and as a result you see a wide mass range. There is also another channel which people talk about is the black hole binary formation near the AGN disk or inside the AGN disk, which also favors more high masses as well as higher spins. So the take home message, black hole population, it appears that it's a result of various formation channels because of this multimodal distribution. Of course, they are direct signatures of the formation channels. There are questions regarding the low mass gap, which will get settled when you have more systems. There is also open question with the discovery of 1905-21 about the high mass gap and the subsequent constraints on the stellar evolution models. Of course, there are lots of other factors which decide this, which is the nuclear reaction rate and rotation and lots of things which essentially govern these stellar evolution models. And all these things can be answered only if you have more number of observations which will constrain all of this, which needs complete waveform models with all the complexities. It also needs algorithms which can distinguish massive black hole binaries from the noisy glitches. So there is one idea which we have, which one of my students is putting up as a poster. So please have a look at his poster. Of course, there are improved astrophysical merger rate density estimates with our new population of black holes. With this, what are the future prospects? We are very close to the 4th observation run. It can start sometime in few months. And with the 4th observation run, which is going to be almost for a year, and with that we expect that the I mean all these numbers will go up. I mean typically the distance reach for binary neutron star black hole and binary black holes, everything will go up. And as a result, of course, we are going to see many more systems with stellar mass black hole mergers, binary neutron stars, as well as we are hoping to see few intermediate mass black holes. And that's about it. And I hope we will be able to update you with better algorithms and better strategies in order to look for these massive black holes. With that, I thank you. Thank you all for your attention. I also would like to thank all my teachers, mentors, friends, and students, and and my family, of course. For students, I always list some resources. So I think, yeah, I mean, please have a look at this. There are a lot of interesting things, including music with gravitational waves. I think it's a small music piece which has been sort of constructed using all these binary black hole mergers. Thanks a lot.
Okay, it's lovely. Thank you so much for an excellent talk. And so open for questions. Could we have lights to see hands? If there are any? Okay, Parth.
Very nice talk, Archana. My question is about the spin. What you mentioned is that, well, the spins of the components of a BBH, they could be reasonably high, the curve parameter could be more than 0.5, but you said that eventually, if you look at the remnant, it's most likely low spinned.
Yeah, so I think,
or at least the effective spin is low. That's
I think the effective spin of the remnant, they have seen almost like 0.7.
0.7. Okay,
Yeah,
that's not so low.
Yeah, 0.7 at least. Yeah, I mean, and this has been, yeah, people have been saying that this is consistent with the numerical relativity simulations.
Okay.
So yeah,
right.
so I think that.
So very basic question. So can we definitely say with all the LIGO observation that black holes obey the Kerr metric?
Ah, okay. Yes. So okay. So I think basically, okay, what we do is, which I did not talk about here, is how we sort of test GR, right? So typically there are various ways people test GR, and so far things have been consistent with that. Okay. So I think one of the tests which I think Prayush was mentioning, where we take the signal which is pre-merger and then the post-merger, and try to sort of compare the consistency with that using the GR models. Okay, so which also uses the Kerr solution, and that has been so far consistent. So I think that's all I can see. There are lots of other tests which we do, which also uses the Kerr. Yeah. I think anybody wants to add? I remember Ajit was the one who developed this. Yeah, I don't know whether he's there. Ah, okay, he's there.
Just to add, for them to test GR, then you have to go for a small mass. You cannot go for higher mass. IMBH is of no use.
No, that's true. So in fact, sure. So we couldn't do that test for IMBH. For IMBH, we do basically ring down test, where you are basically just looking at the post merger. But of course, we have not found good candidates for doing good ring down test, because I mean, even with this the ring down signal had just 2 cycles or something, which is, I think we need to wait.
My question is regarding dimension. Is there any signature of higher dimension in this kind of black hole merger?
Who is this? Yeah, so so I mean, again, I think this is again to do with the tests so far we have designed. So all these tests are dependent on the waveforms, and as a result, I mean, we are only checking the consistency of the waveforms with the this thing. So the idea is that if you find inconsistency, then you will go ahead and try to explore other possibilities. So far it's only we just testing the consistency with GR. Yeah.
Hi, I have a naive question about formation of black holes in galactic nuclei here. So you talked about escape velocity being high, that's why the binaries are trapped in the environment, but how does the high metallicity play a role there?
Yeah, I am not an expert on this. So yeah, let me just see. Yeah, basically the metallicity depends, drives the wind, right? So you're basically the mass loss is decided by the metallicity, and as a result, like I mean, if you have high metallicity, you have more mass loss. As a result, you have less sort of mass. So I think, I mean, that's how it at this level it sort of plays a role.
Okay.
Hi, thanks for the nice talk. So I had a question. So the mass cap at the higher end is going to be filled by these dynamical mergers, right? That's the expectation. So do we actually have some theoretical prediction for what that shape should be? From like what fraction of stars are in globular clusters or something?
Yeah, I have no idea about this. So, but I think what I know is that, I mean, these models essentially, yeah, I think there are some predictions. So, for example, I know there is some prediction for the AGN disk model. They have some predictions about how, yeah, I think you can look at the papers by Yang, Bartos. Okay, so they have actually the prediction how the power law might be. They also have prediction about the eccentricity, which because they expect that systems would be more eccentric, and so I think that's. But I think all these things are, I think they are quite new, because after the discovery of 1905-21, I think there are all these new models they are also trying to sort of, yeah. So,
Thanks.
Hello. Yeah, thanks for the nice talk. So I would like to know, like this simulations has been done for the circular, keeping in mind that the eccentricity is 0. So if you are including the eccentricity, so basically when the stars are orbiting, the eccentricity will change with time, right? And like you have to like assume some initial value of the eccentricity.
Yes,
so
that's right.
how can you fix the initial value of the eccentricity? And if you input the eccentricity,
you try to probe the initial value of the eccentricity. So you say when we are trying to detect it, so I am only talking from the detection perspective. For waveform generation perspective, I think Prayush is the right person. Okay, so for the detection perspective, you essentially try to probe at a given frequency. So you ask a question that if something inside if it is eccentric, then at a particular frequency, what would be the eccentricity? But I think when they develop waveform models, I think they assume a distribution of initial eccentricity, and of course, I think this is all. I don't think so. We have available waveform models for. I mean, there are few waveforms available for high mass system. I think that's why that work was done. The work which I showed about the alternative interpretation. Yeah, this one, the second one. So here essentially they had some sort of one of this numerical relativity collaboration. They had few eccentric waveform models, and then they did some kind of extrapolation and then try to probe this. But yeah, but I think otherwise you take some distribution of eccentricity and then run numerical simulation, generate waveforms, and which we use. So that's how it happens.
Thanks.
Hello. May I ask one simple question, madam?
So let's have this the last question.
Madam, only one question.
Yes, sure.
So in your research, mainly madam use chi-square distribution, right? So what will happen if you use normal distribution in your research?
Which distribution?
Normal distribution.
Normal, what is it?
Normal distribution. Mostly madam use chi-square distribution.
Yeah. So for what?
So in your distribution, right? You have used chi-square distribution.
Okay. Wait. Yeah. No, that is not that chi-square. Sorry about that. I think you are talking about this one.
Yes, chi-square.
Yeah. No, sorry. So we call it as chi-square. So basically here I didn't spend time, but I'll tell you what we do here.
Okay.
Yeah. So if you take this signal,
okay,
then essentially it has some spectral feature, right? So the frequency essentially.
Okay.
So we tile it. Okay. And then we ask a question whether the spectral content in the data, whether it is consistent with the template which it matched. Okay. And then if it is, then we subtract it in some sense from the data, and then the remaining distribution should obey a chi-square distribution, because you assume that the remaining thing would be just noise.
Okay, okay.
Okay, and we use this as a veto. So if let's say you have some noisy glitch, which is our template is basically latching on, and if I repeat the same exercise,
okay,
then my chi-square will be very high.
Okay.
Because there will be some remnant, because it will not.
If chi-square is very high, I think it tends to normal distribution, normal Gaussian distribution like that. I think so. That is why I am asking.
Yeah. So basically, you assume. So what happens is, if you subtract the signal completely,
okay.
Then it's like a Gaussian, many Gaussians, right?
Right.
Right. So that's what happens, which obeys a chi-square distribution with some degrees of freedom.
Okay.
So we use that feature to develop this veto, basically.
Okay. Thank you, ma'am.
Okay, so let's conclude the session and thank Archana once again.
Okay. Thank you. Thank you very much.